Yeah, hello. My name is Tobias. I'm a master's student at TUM, and yeah, like Alex said, I worked on KZG before in Isabel, but now switched to Lean, and it seems like this talk is going to be more a bit about functional commitments than KZG, but I assume most of you know KZG, so I hope that's fine. Let's get right into it. First of all, what do I mean by functional commitments? I mean the definition introduced in this lovely paper titled On the PHP Security of Succinct Arguments from Functional Commitments by Chiesa, Guan, Knabenhans, and Yu. And I want to mention Christian Knabenhans in particular, who's been my advisor for this work. So yeah, thank you to him. And what they do in this work is they introduce functional commitments as a generalization over polynomial commitments, vector commitments, linear function commitments, and so on and so forth. And how it works is you have in a functional commitment scheme an abstract query class which you can essentially instantiate to obtain a PCS or a vector commitment scheme and so on and so forth. Since this is RClip day, let's jump into the definition in RClip. It's really straightforward. A functional commitment scheme is made up out of three components: a keygen function, a commit function, and an opening. And the opening is really where the interesting stuff happens. Keygen, commit are just your typical functions as you know them. First of all, it's an interactive protocol. So we have a protocol spec which you can use to describe how many rounds, what messages to send, and so on and so forth. And then, of course, with this interactive protocol, we want to prove that our query and our response are consistent with some commitment. And this is where the query class stuff comes in, right? You can see the query and response types, they are dependent on some Oracle interface. This is really just a query class. And it does a bit more than give you just the query and response types. It also gives you essentially a way how to answer queries. So here's the query class for prime field polynomials, which we use for the KZG. And as you can see, it's fairly simple. Query type is a prime field element. We answer prime field element queries with, again, a prime field element, namely by evaluating a polynomial, right? Pretty straightforward. So now, the main property of functional commitments is function binding, right? And I stole this graphic from Christian's talk from last year, and as you can see, what it says is that function binding on a spectrum from evaluation binding to extractability lies somewhere in between. Intuitively, what it says is, if you, again, imagine these query and response pairs as being part of a kind of a relation, for example, the relation of valid evaluations of polynomials, then what function binding says is that no adversary can create values that are divergent from this relation, but still accepted by the verifier. So maybe you ask yourself now, okay, but why function binding if we have extractability and need that for our favorite soundness properties, for our favorite snarks? And that is a result from the paper mentioned earlier. Actually, you don't need extractability. Function binding suffices to, for example, prove your favorite soundness property about your favorite Planck snark or whatever. Yeah, and now we want to prove, of course, since it's RClip day, the definition of function binding in RClip might look a bit confusing at first, but trust me, it's really simple. I know it's a lot of boilerplate. I'm sorry, but First thing, of course, we have to generate the value. So we go in with a keygen, then we let the adversary run to give us the commitment, the query, and the response, and then we let the interaction run to essentially get the verifier value. So if he accepts or not, and then we go on and check that, of course, that the verifier accepted all the values and that in fact there exists no underlying data that would have created these query response pairs honestly, so essentially the relation check. Right, so now we want to prove function binding for the KZG, and concretely we want to reduce function binding to the RSDH assumption in the standard model. It turns out this proof is not entirely straightforward. There are firstly multiple cases, and one case in particular is a bit difficult. So given this and the fact that RClip is still evolving, as is VCVIO, we try to come up with a proof that is, or like a approach that is as stable to changes as possible. And for that, we came up with a somewhat more general approach that formalized proofs like this. And I think most of us know this, right? Most paper proofs, they follow this paradigm of assume an adversary is successful, then we can use this adversary to break some hardness assumption, right? And most often what they show, or what they what they mean or what they show is that assuming the game conditions on the left-hand side of the game, right, that they have a reduction that somehow turns this game value, so the right-hand side of the game, right, into something that breaks some hardness assumption. So if you think about it, this is something very much acting like an implication. Oh, sorry, I forgot to switch that. Oh. Yeah. And now in our clip, we have this nice monotonicity lemma, which essentially relates an implication on the game condition sides to the complete game probability. And now I think you kind of seen where I'm going with this, right? So essentially the idea is to, if it's possible, try to take this paper-proof reduction map and somehow express it into such an implication statement, which you can then use the monotonicity lemma on to end up with a result like the one in blue above. And it turns out if you have this implication statement, there's a relatively simple proof plan which you can use to essentially get this blue statement above. Right. And now I know what you're thinking. Not all proofs are structured like this. You cannot always express them as implications, and you're right, of course. But still, I think there's a decent amount of proofs for which this is possible, especially for proofs like the ones for non-interactive functional commitments. And really, I think that this is the way to go for these proofs because of 2 or maybe 3 reasons. Firstly, with this whole implication structure, you're typically able to go pretty close to the actual paper proofs just because you have this whole assume adversary is successful and assume the left-hand side of the implication thing, right? And then secondly, at least from my experience, it turns out that AI formalization tools are way better at doing proofs in this very mathematical implication regime than doing game hops where you have monads and reasoning about state of oracles and all that. And then thirdly, you really minimize the breakage area. If RClip or VCVA or something like that gets refactored, you usually don't have to refactor much of the implication statement. It's almost abstracting the real reduction from the game hops. So yeah, I don't want to show you the whole implication statement because that is maybe a bit difficult. But what I can show you is the execution of the proof plan for the function binding for the KZG, and that is really kind of simple. We start, of course, with applying the monotonicity lemma. So we start out with the function binding game and the function binding condition, and show via the implication that the RCH condition with a reduction map is implied, right? And then we drag this reduction from the left-hand side, so from the game condition level to the game level. Sorry, from left-hand side to right-hand side, right? And then we just go in and reorder this reduction applied to the game level, on the game level, into the RCH game played by a reduction adversary, which essentially simulates the function binding game. And then as a last resort, we just say, okay, since this is an RCH game played, the probability of this being 1 is less than or equal to the RCH error. Okay, in all reality, we had to do one more game hop in the beginning, but this is just because the reduction from function binding to RCH condition needs a bit more values than the function binding condition. So that is one extra step you might have to take. But other than that, it's fairly simple. That's the point. Right. Now I don't know how good am I on time. Pretty perfect. Then I can finally talk a bit about KZG. So what I didn't show you last year in my Isabel talk was the KZG definition, and that was because honestly, it wasn't that great. There were a lot of things I had to define prior to defining it, and this is different in Lean, right? If you take a look at this, all functions virtually, except for the term of exponents function in the generate SRS, are already existent functions that could be used either from computable polynomials or from mathlib or from Lean standard library. So this definition to make is fairly straightforward because of the algebraic nature of the KZG, I guess. Now, I know the KZG is not the most complex polynomial commitment scheme or functional commitment scheme, but I would invite you to try to just write down your favorite, maybe a bit algebraic functional commitment scheme and see how far you can come. Because, like I said, with all this math development in Lean, I think there's really good foundation for that. So, I think that is everything I wanted to tell you today. So, thank you very much. I'm happy to talk everything about RClip and functional commitment scheme. So yeah, please come talk to me. Thank you.
Do you want to switch over, Julian, if you want to switch machines? And then whilst Julian faffs about